So hello everyone. Now this is topic 9, which has to do with process flow measures. And now what's very important in the topic is to understand the three very important measurement that we will take. The first one is the flow time. So the flow time right here. The second one is the flow rate, which is R, and inventory is I. So let's look at the check-in process at an airport. So when you go to check-in, there's customers walking in, check-in process, and after they do the check-in, there's customers leaving. And in the middle of the process, there are customers stuck in the process or being served or waiting. We call that inventory I. The rate at which customers come in and leave, we call that R. And then the time it takes for so a time and an average customer spends in the system from the beginning walking in to walking out is T. So that's flow time T. While R is the flow rate and inventory is I. And all these numbers are average numbers. This is very important to remember that these are all average numbers. So a process, we have inflow in a process and outflow in a process, and in the process we have, it could be, as we said, it could be product, it could be customers are stuck in a process in terms of inventory. Now when the inflow exceeds outflow, so the inflow is much greater than the outflow, and you see this in places in the early morning where you have more customers coming in than leaving. In that case, inventory will increase. So I will increase in that case. So in the first case, I will increase. Now, when the outflow rate is higher than the inflow rate, so more people leaving the process than entering the process, then inventory is gonna go down. Now, what we just mentioned is all in the short term. In a long term, we get more of a stable process where the inflow rate, so in a process, the inflow is going to be equal to outflow. So R is going to be the same whether you measure it at the inflow or you measure it at the outflow. And we call that throughput. So that's a new terminology, we call that throughput. So again, we call R, it is the average inflow rate, the average outflow rate, and it's also the throughput of the system, of the process. And now we get the same definition in terms of T and I. But what's very important about a stable process is that we get to use Little's law. Little's law is basically this very important relationship that is going to relate R, T, and I. So whenever you have one of these three variables not known, you could actually calculate it using this equation. So let's see an example on Little's law. Now, this is the time when you should pause the video and read the example and try to do it on your own before you could play the video again. Now, we have a toy manufacturer. That toy manufacturer had a throughput rate of 30. So this 30 is basically R. And it takes 0.5 hours for a toy to go through the process. So we have 0.4 hours. It takes time, and we know that this is T. This is the time it takes for the flow unit to go from the beginning of the process to the end of the process. So that's T right here. How many toys on average how many toys are on average in the process? Now they're asking us for I. What's stuck in the process on average is basically I. So this is the throughput. This is the flow time. We don't know inventory, so inventory is our unknown. So we just use our equation I equals to R times T, and we get 15 toys. So let's see another example. Now with this example, again, pause the video, read the example, try to do it on your own, and then play the video again. So we're looking at a local deli where people arrive at a rate of 30 per hour. So that's basically your R. Remember, arrival rate and output rate has to do with R. On average, there are 8 people waiting in the line to be served. So this is people inside the process. So we're looking at I. Once a person gets to the counter, it takes average 5 minutes to be served. What is the flow unit? So the first question is, what is the flow unit? And in this case, the flow unit are basically people. The flow units are people because people are coming into the deli. Now let's draw the process. Now the process here is a little bit more complicated. We have two different things, two different processes. We have the waiting. So when you walk into the deli, there is waiting, and then there is the actual service. Now with the check-in process, when we talked about the check-in process, we didn't go into detail. We just said the whole check-in is a process. For this, we have two different numbers, one for waiting, one for service. So we have two different processes, and there's people coming in, waiting, and once the waiting is done, they get serviced. The service takes 5 minutes, and then they're out. So now the question asks, how long does a person wait in line? How many people are being served on average? How many people are in the deli on average? How long does it take a person to go through the process? The challenge in this problem, is that we have a process broken down to two processes, and we're going to see a lot of example like this. We're going to see later on the hospital example where we have maybe 6, 7 different processes. And so it's very important to us to understand that there's two different elements or different processes, which are the waiting in line and the actual service. So we've shown that in the diagram where you have this is waiting, and this is service, and then you're out. You see a lot of our examples, we use triangle to basically represent a waiting process, and square for a normal process. So in the deli, we have this situation here, and they're giving us numbers. So for example, there's 8 people waiting in line, so we know I for the triangle, the waiting is equal to 8. And we know that the service takes 5 minutes. So we know I for the first process, and we know T for the second process. And very important, R is going to remain the same, because with Little's law, we know that in a long run, in a stable process, the inflow is equal to the outflow. So R is going to be the same everywhere. So the rate of customers walking in and moving through the process is going to be the same. Now, very important, this might change when the flow unit change, and we will see that in later examples. So now we go on. So we'll calculate R in terms of minute, because all our other numbers are in minutes. So if we have 30 per hour, we get 0.5 per minute. We just divide by 60. Flow time is 5 minutes. We've already mentioned this. and the people inventory in the waiting line is 8. So if we draw a table, then if we look at the different parts of the process, we have the waiting line, which is 1, and then being serviced is 2 in terms of the process. We know the inventory waiting in line, we know the throughput, then we could right away calculate the T using the equation. So the equation T basically is equal to I over I over R, and this is just rearranging the equation. And by calculating, so when you go 8 divided by 0.5, it's going to give us 16. Now, the problem becomes really simple when we organize ourselves and we think of the process in terms of two parts, waiting line being served. That's going to help us in answering the question. Now, being served, we know that the R is still the same, 0.5, and we have the time. Now, what we need to do is calculate the inventory, and that's what the question is asking, how many people are being served. So R times T, which is 0.5 times 5, is going to give us 2.5. Okay. Now, if we want to know the total number of people in the deli, which basically means waiting line plus being serviced, then we have to sum these two numbers. The throughput, we don't sum the throughput. This is very important. This is a common error students make. You don't sum throughput. You only sum inventory and you sum the times too. So if we want to know how long the whole process took, is again, we have to sum 16 plus 5, 21. Now, again, here we have a process. We divided it into two parts. You could think of it as two processes. But we're looking at it here in terms of parts. So two parts. Throughput, we don't add throughput. This is very important. Throughput is a rate. You don't add rates. We add the inventory and the flow time for the overall process. Now, when the flow unit changes, and we're going to see that later in other questions, that's going to create a lot of problems for us, and once we get to this question, we'll show you how to deal with that. Now let's see question number, this example, an insurance company. This is a straightforward example. So the flow rate of basically here, the flow rate is money, sorry, claims. So you have 10,000 per year, and the average processing time is 3 weeks, and this is T. So how many claims are being processed? Are being processed at any given time. So how many claims are in the process? So if we think of this, so this is an insurance company that's processing claims. So their output and input is basically how many claims are they're getting is R. And that's what we said. So 10,000 per year. And the average processing time is 3 weeks. So this T is equal to 3. And but what we don't know is inventory, how many claims are being processed at any given point in the process. And to do this, we just use the equation. Since we have R and T, all we have to do is convert T to years, because we have it in terms of weeks, and R is in terms of years. Again, it's very important to make your units match. So if one of your units is in hours, the other there. So if here in this case our R is in terms of years, so we have to have our flow time in terms of years. So again, this is another question. Again, pause the video so you could read the question and try to absorb it and try to do it on your own. So let's get to it. So we have a manufacturer that bills about $300 million worth of cellular equipment per year. So this is our R. So R, a lot of times R is gonna feel like the annual demand, the annual. So remember when we in your COM 225 when we had the annual demand for something in these inventory problems, that annual demand is really R. And in this case, R is here. The average amounts in accounts receivable, and this is going to be I, inventory. How much time elapses from the time customer is billed? So they're looking for T. This is what they're looking for, this question. So we know what R is, we know what I is, and then we just calculate T using, again, little law equation. So little law equation is going to allow us to do so many different problems. So far we've learned the throughput, which is R, flow time, which is T, and inventory, which is I. But there are other interesting things that we have to learn in operations. We have the takt time and inventory turnover. And basically, takt time is really the time between one unit till next unit in production. So basically, think of it, if you're standing outside of production line and you're timing the time between one product and the consecutive, this next product, that time is really takt time. And that takt time works out to be 1 over R. So it's the reciprocal of R. So whatever R is, if you take the inverse of it, you're going to get takt time. And if you're doing this, and if you substitute this into the Little's law equation, then we're going to get takt time equal to T over I. Inventory turnover is basically very important, is how many times the inventory is sold and replaced. So how many times are you selling and replacing that inventory during a time period? So if you have a turnover of 3 in 1 year, it means that you sold your inventory 3 times and you replenished your inventory 3 times. And that's basically the reciprocal of T. So takt time is the reciprocal of R. Inventory turnover is the reciprocal of T. And when you take into account Little's law equation, then it's basically R over I, just substituting the 1 over T into that equation. And so now let's take an example on takt time. So we have a medium car manufacturer which has an inventory. So this is our I. First of all, the takt time equation is T over I. And all these equations, remember, all these equations are going to be with you. Most probably you will write an online exam, final examination, which means you could write down all these equations, prepare them when you're doing the examination. So we have an inventory of 150,000 cars. That's how much they told us the inventory is. And the time is, they're telling us the duration is 2 years. So we know that there's 8 hours per day, and we know there's 250 operational days per year. So we could get the T, the overall T, which is 4,000. And then takt time would be T over I, and it's going to be 4,000 over 150,000, which is 0.026 hours per car or 96 seconds per car. Now, don't mistake this number. Don't think that it means that it takes 90 seconds to produce a car. That's not correct. What that means is that when you're producing these cars, if you're standing outside of the production line, every 90 seconds, the production line is going to spit out a car. That's basically what it means. So now we get to the big real problems. These problems are basically gonna show us how we're gonna use what we've learned in real life examples. And this example comes from the medical system. So this is the time again to pause the video and read the example and try to at least set up the problem. So in this case, this is obviously this is in the service industry. We have a hospital, the ER room in a hospital, and we have patients entering the ER room to get some care. And then so the patients come in and there's two alternative outcomes. Either a patient is seen by the doctor and they realize that the patient needs to be admitted to the hospital. And then there's the other alternative where the patient actually does not need to be admitted to the hospital and a simple prescription is written and the patient goes home. So they're telling us that 50 people arrive at so we have 55 people arriving in the ER room, and they're telling us 10% of them are admitted to the hospital. On average, 7 people are waiting to be registered. So we know that obviously when they come in, there's registration, and that registration takes 2 minutes. And so 7 people are going to be waiting to be registered. And then once they're registered, there's 34 people waiting to be seen by a doctor. So if a patient ends up being a prescription patient, so a patient that does not need to be admitted to the hospital, they will spend an average of 5 minutes. While for those that are going to be admitted to the hospital, they're going to be spending 30 minutes with the doctor. We're assuming that the process is stable, which basically means we could use Little's law. And we have the first question asks us, how long does a patient spend in the ER room? So the first thing we need to do is draw a process map. This is the most important thing. And here is the process map. So we have to basically absorb everything we just read and basically draw a process map based on what the question says. So we know that there is so again waiting is annotated with triangles. So triangles for waiting activities or waiting stages, and then the actual registration is a triangle and doctor visit is a triangle. Now, also before we go into the drawing of the process, we have to understand in this question, the flow units, at first, they are the same. Patients are entering the hospital, it doesn't matter. So a patient before the checkup, we don't know which patient is a simple prescription patient and which one is a potential admit patient. So, but once this is identified, then the flow units are going to be, we're going to have two different flow units. Now, this is very important. This is quite different than the other questions we've seen before. So we have, first of all, there is the customers walking in. So maybe let's have it in red. So we have, or maybe yellow is better. So here is we have the buffer. So the patients, they enter, they're waiting to register, and they told us that there is 7 people waiting to be registered. And then after that, we go into they go into the registration. So after the waiting, they get to register, and that will take 2 minutes. And so that's we have registration, and then we have another waiting. And again, we're just basically interpreting the question. That's all we're doing. We're just drawing what the question said. So we're drawing the process. So then we have another waiting station, and then this is the waiting to get seen by the doctor. And they told us that there is 34 patients in waiting, so they are in inventory. And then we go on to see the doctor, and here we get two different times. One time is for if a patient ends up being a simple prescription patient, and then we have if the patient turns out to be, and that turns out that that patient needs to be admitted to the hospital. Now we see 10% here and 90% here. Now this is so this is why we're showing 10%, 90%, because here the flow rate is gonna be specific. So we're gonna have a flow rate for potential admits and flow rate for simple prescription. So initially we had the flow rate of 55. So because that's what they told us there's 55 people arriving in the ER. So that's initially, but once we get to the doctor, we're gonna split into 10% potential admits. So that's gonna be 10% of that flow rate, and then the simple prescription are gonna be 90% of that flow rate. So so this is basically the process map. So what we want to do is the question asks us how long does a patient spend in the ER? So we're going to add all the different times throughout the station. So we're going to look at the time they are in buffer 1, the time they are in registration, how time they are in buffer 2, the time they spend with the doctor, and then we're going to use a weighted average to know, because we're going to have two different because we have two different flow units. So it's a stable system. A flow rate is 55. We'll convert it to hours. The flow rate for potential admits, we're multiplying 55 by 0.1 because we know there's 10%. So we're going to get 5.5 per hour. So again, we are going to have a flow rate for potential admits and a flow rate for prescription. So the flow rate for prescription is 55 times 0.9, and we're going to get 49.5. So we have two different flow rates, one for the potential admits and one for the prescription. So now we're basically going to be looking at all the different stages, and we're going to calculate the time for each stage. So we start with buffer 1. And we know at buffer 1 we have 7 patients in the inventory. R is 55 per hour. At this point, the flow unit is still patient. We didn't go specific into whether the patient is potential admit or simple prescription, because that hasn't been decided yet. So R is 55. And so to calculate the T is we're just going to go I over R, and it's going to give us 0.127 hours or 0.7.6 minutes. Now then we go on to registration. Now at registration, the time is already given to us, so it's 2 minutes. But here we're calculating the inventory because we will need it for later questions. So now in the next stage is we have buffer 2. So we have buffer 2 and doctor. We've already calculated buffer 1 and registration. So for buffer 2, we know what I is. So I is given to us 34, and we know the flow rate is still the same, 55. So the time would be just I over R, and we get 0.62 hours. Now we go into doctor time, and here the times again are given to us. For potential admits, T equals 30 minutes, and prescription patient, T equal to 5 minutes. So now we basically we have to basically add all the different times. We have to add all the different times for potential admits, buffer 1, registration, buffer 2, and doctor. So we're just adding the numbers we've already calculated, and we're going to get 76.7 minutes. And for prescription patient, we're again adding all the different numbers, and 7.6 to 37.1 plus 5. Now notice the only difference between the potential admit and the Prescription patient is the doctor time because that's the only difference between them. And we're gonna get 55.7 minutes. So on average, because they're asking us they're asking us how long does a patient spend. So they're not talking about the potential admit or the prescription patient. So in general, the patient as a whole. So for this, we have to take 10%. So we're going to do like a weighing average because we know 10% of the patients are going to be prescription patient. Sorry, 10% of the patients are going to be the potential admit patient. So we're going to multiply the time we got from potential admit by 0.1. And then we're going to add to that 90%, 0.9 times 51.7. Again, this is 0.1 and 0.9, not 10%. So we're multiplying by the ratio. And if we do this, we get 54.2, and that answers part A of the question. So an average patient spends 54.2 minutes. So at this now the question we're in part B, which asks part B asks us how many patients are being examined by the doctors. Now at this point we have at the doctoring activity we have to take into consideration that we have two different flow units, one which is potential admits, so we have the potential admits, and also we have the prescription, simple prescription admits. Each one of them is going to come at a different R. And remember, we said for potential admits, they're 10% of 55. So we multiply 0.1 by 55, we get 5.5. While for prescription, we get R 49.5, which is 90.9 times 55. So we know the time for each one of them. And what we want, we use the equation of I equals to RT. So basically, so we know what R is, we know what T is, so we calculate I for the potential admits, which is going to be 2.75 patients, and for prescription is going to be 49.5 times 5 divided by 60, and that's going to be 4.125 patients. So the total inventory, the total number of patients at the doctor are going to be the sum of these two numbers, and it's going to give us 6.865. So the last part of the question asks us how many patients are in the ER. So basically at this, we're just going to look at all the different stages and sum all the different inventories. So we know that there's inventory in buffer 1 is I7, so that's it. And for registration, we've calculated that previously, 1.83. And we know for buffer 2, it's 34. For the doctor visit, we've just calculated that sum in the previous slides. So when we sum all this, we're going to get 49.695 patients. So I remember all these numbers are average numbers. So that basically concludes this question, which is a very interesting question. So we've seen a real life scenario of probably some of you have experienced going into ER and seen this sort of process where you have to register, wait to see the doctor and all that, all these different steps. So we see right here is basically the implementation of little law in a real life example. So basically, let's move on to the next question. So for example number 8, we're adding, it's basically the basic example for number 8 is 7. So we're continuing from example 7, but we're adding a triage nurse. So there's a nurse that is the nurse, and the nurse will decide who will be the simple prescription and who would be the potential admits to the hospital. So our process is going to change a little bit. So we are adding a triage nurse here, and then we have two different waiting scenarios, one for potential admits and one for the a simple prescription, and then the doctor sees the potential admits, knowing that they are potential admits, and then the doctor sees the simple prescription, knowing that they are simple prescriptions. So the process map is gonna change a little bit, but the overall procedure, we're still looking at stages, and we're calculating the inventory or time for each stage depending on what the question is asking. So how many patients will be in the ER? So they're asking for inventory. So again, we're doing the same thing as we've done in the previous question. We're going to be looking at the inventory in each station, in each stage. So in buffer, registration, buffer 2, triage nurse, buffer 3, buffer 4, potential, and the doctor visits, and we add them all up and we get an overall number for the inventory. Now we have to remember that the potential flow rate for potential admits is going to be 10% of the overall flow rate, while for prescription is going to be 90% of the overall flow rate. Throughput is we're gonna convert the throughput in terms of minutes because all our numbers are gonna be in minutes. So we're using the I equals RT formula to get the inventory. So we sum all the inventories. So we have 20 patients in buffer 1, so they're giving us the inventory here. Registration, they're giving us the rate and the time, so we use that equation to calculate the inventory. Buffer 2, we know there's 5 people. The triage nurse takes 1 minute, so we convert that again to an inventory by multiplying it by the rate. And buffer 3, we got a number here. The potential admits, we know it's 30 minutes. So we 30 times 0.1967 times 0.1 because we want to rate it for the because it's 10% for potential admits. Buffer 4, there's 15 people. Simple prescription, again we have the time and we have to convert the time into an inventory, and then we add all of them up and we get 50.627, the total inventory. Now we're going to assume, we're assuming again 90% of all patients are simple prescription. How long does a patient spend in the ER? So there's a shortcut to answering this question. So instead of going in every stage and calculating the time and just adding, we could just look at the overall system, and we know we just calculated the overall inventory, which is I that we calculated in part A, and we know the flow rate coming in and leaving the overall system, the whole process, all the processes is 50.627, sorry, 0.9167 because we converted it to minutes, and we're dividing by what we just calculated in part A, which is 50.627, and we should get 55.323 minutes. Now, if you were to calculate the time for each station, and so we calculate the T's and we add them all up, and we take into account the weights that 90% of our patients here are going to be simple prescription and 10% potential admits, you will get the same answer. Now part C of the question is asking us how long would a potential admit spend in the ER. Now what we're going to do is we're going to add up all the different stations or stages that the potential admits will go through. So the potential admit will go through buffer 1, registration, buffer 2, triage nurse, but obviously the potential admit will not go through the simple prescription path. He or she will go through the potential admit path. So we just add all these up, times in all these stages, and this is actually in Excel. This shows you the times, and we add all these times, and it's going to give us 71.18 minutes. This is the answer. And how long a patient who has a potential admit spent in the ER. So this is example 9 now. So as I said, this is always the beginning of the example. It's a good time to pause the video and try the question yourself. So now we're talking about a car rental company. They do two different car rentals, short-term and medium-term. The short-term takes 0.5 weeks on average, while the medium-term takes 2 weeks on average. The short-term is 200 cars rentals, while the medium-term 100 rentals, and each of them coming at a different rate. The short-term $200 per week, and the medium-term is $120 per week. Approximately 20% of the cars returned to the customer would need repair at a cost of $150. And so basically cars, 20% of the cars that the customers return, they need to be repaired, and that means they would stay 2 weeks at the repair shop. The remaining cars, which would be the 80% of the cars, would be washed and cleaned at $5 per car. They're telling us an average 100 cars are waiting to be cleaned, and cars are rented as soon as they are available. So the question is, we're asked to find the throughput and inventory for every and flow time for each stage. So we have 3 stages here: the stage of the customer using the car, then the cleaning stage, and also the repair stage. What profit does the company earn per week? So they're asking us about the profit, and then they're giving us 2 alternatives that we want to choose one of which. So let's draw the process map. We have the customers using the cars, and then from there on they either get repaired or cleaning. Okay, so we have 3 stages: customer, repair, and cleaning. So we want to calculate, the question asks us to calculate the throughput, inventory, and flow time. So let's calculate. So now we have different R's. We have an R here that is different than the R here, and we have an R here that's also different because the flow units have changed. R1 is cars to be repaired, R2 cars to be cleaned, and the first R is the R. So the first R right here is number of cars that the customers are using. So there are basically very important. Let's collect some information that we need. So we know that there's 100 cars waiting or being cleaned. Here we're going to assume that when we say 100 cars waiting, that's all the cars in the system, whether it's cleaned or waiting, because we don't have any other information. So now, first of all, we know that our first R, our R coming into the customers using, are going to be, we have 100 medium term and 200 short term. So both of them together, our first R is going to be 200 times 100. So this is 2, which is equal to 300. Now, based on this, we know 80% of the cars are going to be cleaned, so we could get a flow rate of R2 here, which is cars to be cleaned. Now, and so we have one more piece of information in that table, and then we know the car is going to repair this 20% of that 300 number, so we got 60, and we get that number. So so the inventory for the customers, now we know that there's 200 cars short term at 0.5 weeks. So we go 200 times 0.5. So we know there's 100 for short term on average, and then there's the other rental is 100 rentals at 2 weeks, so 100 times 2. So because we're looking at how many different days the cars are being used, so we get the 300 cars in inventory. So now we could calculate that we have everything needed to calculate. They told us also of another piece of information. It takes 2 weeks on average for repair. So 2 weeks on average on repair. So we get this number here. So now we could just use our IRT equation to calculate everything else. So for the so let's start for repair area. We just go IRT 60 weeks times 2 weeks, we get 120. For this question, we know that the flow time, we were missing the flow time. We don't know the flow time for the cleaning area, how long. We know there's 100 cars in the system, there's 240. So we just use again the IRT to calculate T. So T in this case is I over R. So we get 0.42 weeks, and this week with same logic, we get the 1 week here. So we've just answered the first question. We identified the throughput, inventory, and flow time for each stage. So let's continue to part B, where they're asking us what profit does the company earn per week. So let's think about, now we need the number of cars owned by the company altogether. So we know there's 300 at the stage where the customer are using, while 100 are being cleaned and 120 are being repaired. So we have 520 cars in total. And number of cars, which is R, being used by the customer is also, this is the number of R, and also it is the number of cars being used by the customer. So the revenue per week is, we're looking at the number of cars in short term times that rate. They're getting $200 per week. Then we're going to be looking at the medium term, the number of cars in medium term, and that rate they're getting. So we've already calculated these two numbers in the previous slide. We got 100 being in short term and 200 for medium term. So we just multiply by a rate to get 44,000 per week. So now, but the question is asking us for profit, not revenue. So profit means revenue minus cost. So let's look at all the different costs that they're incurring. There's the cleaning cost, repair cost, and depreciation. So the cleaning cost is basically, we're using the rates. So we're using the rate, how many the rates of the car are the throughput for within the cleaning, and that happens to be 240. So 200 times 5 gives us 1200. Repair cost per week, we're going to be seeing 60, that's the throughput, times the rate they're giving us in the question, 150, so we get $9,000 per week. For depreciation, all the cars are depreciating across all the stages, and here we're using inventory, not throughput. And this is very important. We have to remember, whenever we deal with depreciation costs, we have to use the inventory number. So all cars through all the stages is going to be 520. So we're using 520 times that $40 that they gave us in the question. So we get 20,800. So now profit per week is we're taking that revenue, we got 44,000, and we're subtracting from it all our costs, and we get $13,000 per week. So the last part of the question is asking us to find the cheapest alternative of the following: decrease time in repair from 2 weeks to 1 week, decrease cost per repair from $150 per car to $120 per car, keeping it at 2 weeks. So now we just have to calculate both options. So the first option, when we are reducing repair from 2 weeks to 1 week, we get 2,400 in terms of savings, while here we only get 18. The second option, we get 1,800 in terms of savings. So decreasing flow time and repair is more effective. So a famous hotel chain caters to both business and leisure travelers. 1/3 of travelers are leisure, and they would stay 3.6 nights. And obviously the rest are going to be the business travelers. So they're asking us all different questions about again, the same idea with the I, R, and T. So let's move to the first part, do the A part of the question. So here, assuming there's 135 guests check into the hotel, and average how many guests of each are in the hotel. Now, in this point, the very important thing we need to realize that there's two different flow units. There's the leisure travelers and business travelers. So you're gonna have two different R's. So two flow units. So we have business and leisure, and we're gonna have two different R's. So for business, we're gonna multiply by 2/3 because we said 2/3 of all the guests are going to be business, while 1/3 are going to be leisure. So we'll multiply 135. So we get 90 guests by 2/3. So we get 90 guests as business, and we have 45 guests as leisure. And now the question is asking how many guests of each type are in the hotel. So how many guests? We're looking at I, which is I is equal to R times T, and I is equal to R times T for the leisure travelers. And now the times, they're giving us already the time for business, 1/3. So for the leisure traveler, we have 3.6 nights. And so we get right away the 162 guests for that. Now with the and so they basically, so they're saying the leisure travelers spend twice as long as business travelers, and this is why when we take the time for the business travelers, we divide it by 2 because it's half of how much it is for leisure. So leisure, they spend 3.6 nights, while the business travelers, because they spent half of the time, so it's 36.2. So we get 162 guests for business travelers and 162 guests for leisure travelers. Now, part B of the question is asking us about the inventory. How many times per month does the hotel turn over its inventory? So this is the first time we see one of these long questions asking us about the inventory turnover. So before that, we have to remember that we've just calculated the inventory of business travelers, leisure, the rate. And here, this is very important for this question. We have two different processes side by side, each of them with different R's, and the output is a different R here. So we don't have, like we've seen in the hospital example, where patients enter as one flow unit and that flow unit splits into two different flow units. Here, we have two flow units coming in and two different flow units leaving out. So each flow unit is basically unique. And so in this case, we could add the rates for an overall rate for the system because they're asking us for the overall hotel. So whether business travelers or leisure travelers, we're looking at both. So the total inventory of uh, so as for business travelers, or no, sorry, the overall inventory is business travelers plus leisure travel, what we just calculated in the previous slide. We add them up together and we get the overall inventory. So inventory turns are basically RT over IT. That's the equation we've seen before. And here we just add the rates, 90 plus 45, because again, we don't have a case of a flow unit splitting and then merging again. So there's two separate R's coming into two different processes and so on. So 90 plus 45 divided by the sum 324, which gives us 0.4167 turns per day, or we could think of it as 12.5 turns per month. So now we do the last part of the question. So they're telling us the business traveler pays $250 per night, while the leisure traveler pays $210 per night. What is the average revenue the hotel receives per night per room? Now, so we're calculating revenue. We know that half of our guests are going to be business and half of our guests are going to be leisure. So the average rate that they're going to receive half 250, half 200. So on average, per night, per room, so that's per customer, per room is $230. Now, very important, let's recap when it comes to costs. So when we're looking at costs, we multiply by R, the throughput, with the exception of depreciation. When it comes to revenue, revenues, we are also using the inventory, just like we did in the question with the car rental. When we looked at the revenue, we multiplied by the inventory. Okay, so basically that's it for this topic. So stay tuned for other topics that will come in later weeks, more videos to explain the topics. Thank you very much.